Hi students, in the previous class we have learned the derivation of equations of motion graphically, and in this session we are going to describe how to get those equations of motion by calculus method. And the first equations of motion, by definition we have A is equal to dv divided by dt. For this equation we can write dv is equal to a into dt. Now we are going to integrate this both sides of this equation, that is integral of dv is equal to integral of a into dt. We apply the limit. v0 is the initial velocity to the v, and t is equal to 0 to t. And then now on integrating these two, here we are discussing about a uniformly accelerating object. So here the acceleration is a constant, so we will take out the acceleration out of this integral. So 0 to t is equal to dt. So dv from initial velocity to the final velocity, that is v minus v0 is equal to, on integrating this side we will get v minus v0 is equal to, on integrating this a into, we will get t, that is at. So therefore v is equal to, that is the final velocity, v is equal to, and this minus v0 will go this side, that is v plus at. So that is the first equation of motion. Again we have v is equal to dv divided by dx. Again we have v is equal to dx divided by dt. That means dx is equal to v into dt. On integrating this both side again, that is dx integrating from x0 to x, that is dx is equal to integrating v divided by dt, that is from 0 to t. On integrating 0 to t, and now we are going to apply the value of v. Here we have the value v is equal to v plus u at, and this value we are going to apply in this equation into dt. Integrating dx, we will get x minus x0 is equal to v0 into t plus half at square. Again this term x0 is transposing to the other side, so we will get the value of x, that is x is what? X is the displacement here, that is x0 plus v0 into t plus half at square, the second equation of motion. Now the third equation of motion. So we have a is equal to dv divided by dt. That can be written as dv divided by dx into dx divided by dt. Dx divided by dt can be written as, that is the rate of change of displacement, that is v. So this can be written as dv divided by dx into v. We can write v into dv is equal to a into dx. And now we are going to integrate this both sides, integral of v into dv from v0 to v, that is equal to integral of a into dx from x0 to x. Now here the acceleration is a constant, so we will take out the acceleration out, that is x0 into x, a into dx, v square minus v0 square divided by 2. That is, on integrating v into dv we will get from the limit v0 to v, v square minus v0 square divided by 2 is equal to, on integrating dx we will get x minus x0. Now this v0 square plus 2 into a, 2a into x minus x0. Okay, so we cross multiply. Okay, v square is equal to this minus v0 square will go that side, and 2 into a multiply v square is equal to v0 square plus 2a into x, and this is the third equation of motion. So these are the derivation of these three equations of motion by calculus method. We are familiar with the experience that when we are going with one vehicle and another vehicle going in the same direction may overtake us. You are sitting in a vehicle, so the speed of that vehicle is relative to the speed of your vehicle. So that means if both are traveling in the same speed, both will travel in the same direction without changing its position. I mean, both will cover the same distance and same interval of times. But a person who is standing outside the both vehicle, or maybe in a bus stop, so for him the velocity of these two vehicles are relative to another point, and that we call the frame of reference. And for a person who is standing outside, the frame of reference is the surface of the earth. So the velocity of those vehicles are relative to the surface of the earth, or the frame of reference for him. So if the vehicle, they are moving with a different speed, for example, vehicle, it has the velocity a, okay, then two vehicles A and B are moving with the velocities of VA and VB respectively. Then they are covering a distance x a at 0 at the time t is equal to 0, and covering another distance x b at time 0 when time t is equal to 0. So they cover a distance xa and xb after a time t, xa t and xb t. Okay, so this is the initial position of the vehicle A. This is the initial position of the vehicle B when time t is equal to 0. And this is the final position of the object or the vehicle A when the time t is equal to t. And this is the position of the vehicle B at the time t is equal to t. The distance covered by the first vehicle A, xa, at the time t can be written as, what is it say, initial position? The initial position is xa at the time t is equal to 0 plus v into t, then va, velocity of the vehicle A at the time, and the distance traveled displaced by the object B at the time t, or vehicle B at the time t is equal to the initial position of the object B at the time t is equal to 0 plus the velocity of the vehicle B into time t. Now the displacement of the vehicle B from the vehicle B can be written as xBA. Okay, that means the displacement of object vehicle B from the vehicle A, that xBA is equal to at the time t. That means the displacement of the object B at the time t is equal to 0 minus the displacement of the vehicle A at the time t, at xp minus xa. What xa already we have, that is xb we have xb 0 at time t, that is the initial position. Okay, the displacement of object or the vehicle B from the vehicle A at a time t is equal to the displacement of the vehicle B at a time t minus the displacement of vehicle A at time t is equal to t, and that is equal to xb we have already that is xb 0 plus v into vb into t minus xa at 0 plus va into t. xb 0 minus xa 0 plus vb minus va into t. As we seen from the vehicle A, the vehicle B has a velocity vb minus va, because the displacement from A to B changing steadily by an amount vb minus va. The displacement of the vehicle A from the vehicle B can be written as x ab at t, that is equal to, directly we can write from here, that is x a 0 minus x b 0 plus v a minus v b into t. Therefore, we can write v a b is equal to v a minus v b. The same way we can write v b a is equal to v b minus v a. So these are the relative velocity of these two vehicles with respect to another. For example, when we plot a graph, when both are traveling with the same velocity, okay, so this is the velocity graph of object vehicle A, and this is the velocity graph of B. In this case, okay, this is time graph and this is x. So these two velocity graph of these two vehicles are parallel with each other. That means what? Here v, the velocity of object A or vehicle A, is equal to the velocity of the object or the vehicle B. VA is equal to VB. When these velocities of these two vehicles are equal, then these two vehicles are equal distance or equally away from each other at every unit time. So that means they are parallel each other. And the other case, second case, t, that is x. So in second case, one graph is steeper. Okay, for example, this is A, graph of A, and this is graph of B. The condition is that VA is greater than VB. The velocity of vehicle A is greater than velocity of the vehicle B. So that means if the velocity is greater, as we said discussed before, more steeper means more velocity. Okay, so if the graph is more steeper, then it has more velocity. So the VA, velocity of object A, is greater means what? This is more steeper. And here we can see, this is the point where these two graphs, they intersect each other. That means this is the point where these two has the same velocity. Okay, both has the same velocity, and from this point the A overtakes the vehicle B. The third case is both are going opposite direction. VA VB. So here, if this is A and this is B. So in this case, one is going in this direction. That means the velocity is increasing. The another one, the velocity is decreasing. So that means both are in the opposite directions. So then this is the point where this both covers or both has the equal displacement at this the point of intersection. So these are the three special cases of the relative velocity.